So I was just streaming a couple of minutes or a couple of hours ago, and the energy cut off. And I'm gonna continue from where I stopped. So it might cut off again. So if it does, I'm probably not gonna stream anymore today. But I finished reviewing the other books, pictures. I just went over really fast, and now I'm gonna go over this book here. So computer architecture quantitative approach. And this is the where it's more hardware focused, I think, the other books. So just gonna wait to see if it's streaming. So this is a graph showing. I looked into the first pictures here, but I don't remember the other ones. But there is a specific one that I think is very interesting that I'm gonna spend some time. But this is just showing the growth in processors performance for in 40 years, which is kind of interesting. This chart plots program performance relative to the VAX, whatever, as measured by the SPEC integer benchmarks. Prior to the mid-80s, growth in processor performance was largely technology-driven and averaged about 22% per year, or doubling performance every 3.5 years. The increase in growth to about 52% starting in 86, or doubling every 2 years, is attributable to more advanced architecture and organizational ideas typified in RISC architectures. So RISC, from what I remember, is more simplified instructions on the hardware. So I think it means that the hardware has less registers, and like most of the complexity is translated over to the compiler. So the software abstractions do more of the computations, and on the CISC, which is the complex architecture, is encoded, or you have more. The circuitry is more complex, so it allows you to have more instructions, and then this takes some work out of the compiler. And I think x86, which is the one used on most computers, is CISC, from what I remember, and RISC is more for embedded systems, I think. By 2003, this growth led to a difference in performance of an approximate factor of 25 versus the performance that would have occurred if it had continued at the 22% rate. I'm not gonna read everything here. So let's see. This might be interesting. I've seen this Amadeus law before, but I don't remember really well what it's about. So like, I've seen it a bunch of times on different places. I think it's something related to the performance. It's a formula that allows you to calculate performance based on number of instructions and some other stuff that I don't remember. The only improvements was this, or doubling 8 years, in part due to the limits of parallelism of. Oh yeah, it's a formula that allows you to calculate how more efficient a program can be by parallelizing the program. I forgot the exact formula. I probably have a picture somewhere with the formula. So I'm just gonna move on to the next one. So this is like the formats of instructions on the register, like how it works on the bits that make up the instruction. and encode the instruction set architecture. So the instruction set architecture is just basically predefined bits on the hardware that determine what each instruction is going to be. So whoever is designing the hardware is going to select, like when you receive on this funct7 here, from what I remember, like 001, for example, that would be considered as an add or something like that. Like whoever is designing the hardware decides what the bits are going to mean, which instructions they are going to be, by the design of the gate. So based on the bits, they're gonna design the control logics that are gonna change what operation is done on the ALU, which is an arithmetic logic unit, which is a part of the gates that does the computation, does the calculation. Then you have the destination register, the source register. I think this is an immediate register for immediate values. Yeah, like it shows here, I think. The base RISC-V instruction set architecture formats. Instructions are 32 bits long. There are formats for integer register-to-register operations, such as add, sub, and so on. The L format is for loads and immediate operations, such as LD and add L. So immediate operation is like a faster way to add a constant value, for example. So if you want to add 5 to a register, instead of putting the value on the register and then adding, doing the operation of the two registers, you just put the value directly on the instruction. So it's faster. And the load obviously is going to be related to the memory. The B formats for branches and the J formats for jumps and link. So jumps and link is a function call basically. So it jumps to a label and then it saves the return address into a register, I think. So that's after the function is called, it can go back to the place that it was. S format is for stores, having a separate format for stores. All the three register specifiers are D, RS1, RS2 to always be in the same location in all formats. The U formats for the wide immediate instructions. So kind of simple. Yeah, now graph showing the latency improvements of these different parts. It seems that the network is the one that recently has more improvement on bandwidth, and I think yes, bandwidth with latency comparing bandwidth with latency. Log plots of bandwidth and latency. Note the latency improved. Except for networking, we note that there were modest improvements in latency and bandwidth in the other three technologies in the 6 years since the last edition. I think that this is because of the size of the transistor is getting. From what I've seen and I remember, it's just like on the limit of how small it can be without quantum uncertainty, which I don't believe in quantum model, but like the stuff on the Microsoft of the quantum computer, I don't buy that. I don't think that makes sense, because I buy more into the ether model of the universe, and I think it has to be that way because that's the only way that makes sense. Like there needs to be at least a part of reality that is infinite, so it has infinite potential. Because either way you go about it, like it wouldn't make sense for reality to be finite. Because the only way for you to have something finite is if you have a context around that is bigger. So it doesn't matter which way you go, the base layer has to be infinite, and because of that, I think the ether model makes a lot more sense. So where the points of reality that converge towards infinity or diverge from infinity are computationally irreducible. So I think that's what quantum mechanics calls like the quantum computer is like the uncertainty on the like very small particles. I think what's actually happening is that it's infinite potential, and there isn't like quantum state. It's just the wrong model. I think it makes more sense that it is the polarity of the electromagnetic field that creates that is constantly converging or diverging from infinite potential, and everything like the structure of space-time itself is a consequence of the interaction of the act of differentiation on infinite potential. that creates the distribution of pressure mediation, which creates the multifactor geometry of space and time. So space itself is the loss of rest, loss of energy, which is space. So it's the decoherence of infinite potential that creates matter, and the gravity is the acceleration towards the void, which is the lack of space, and that's what creates motion between objects. And from this is my understanding of the Ken Wheeler's model, which I think he got from Charles Proto-Steinmetz and Nikola Tesla. So I think that side of things makes a lot more sense than the quantum model. So I think that the stuff from Microsoft just marketing of the quantum stuff. Yeah, this is again a graph or a table showing performance, the difference in the processors. So I have superscalar. So yeah, the simplest one are pipelines, then have superscalar. Superscalar is when you put like multiple instructions on the same clock cycle. And out of order is when you reorder them as it sounds. So like you create control logics, control like impulses or control logic between the different lines of instructions that allow you to reorder the instructions without having hazards, which means is like you prevent from executing a function that depends on the other one. So for example, if you have a place in memory where there's two different instructions that are going to change that place, obviously you need to maintain the consistency. So you create the logic, the control logic to allow the pipeline to execute that instruction or make the other instruction wait until the other one is executed, depending what kind of hazard it is. This part is very confusing, and from what I've seen on all the materials, and I asked GPT about it to clarify more, but it's still like, because all of them, like on the concept level is easy to understand, but on the actual, like what is actually happening on the gates is kind of harder, because there's different types of hazards you can have, and it's kind of weird, like on the way that they explain on how the hazards are solved. Because if you think about it, obviously there's an infinite amount of instructions, so there's an infinite amount of way to, there should be an infinite amount of way to solve the hazards. But I think that, like, they kind of compromise and just do like a simple heuristic on the pipeline, depending on what kind of hazard it is. And it's just like a control flag, probably, that signals that the same register is going to be used or something like that. And memory hazards, so you have register hazards, which are when you have data dependency on two different register operations. And you have, this is just one type of hazard, but you have other hazards that are on the actual memory that are far more complicated to solve. And I think those kinds of hazards are probably not on the hardware, is solved by the software by applying mutexes. So I think the actual memory hazards are more on the software, that the programmer is going to put the flags using mutexes and locks. And the more simple hazards, which are on when it comes to the operations on the actual registers, then is done on the hardware by creating these control signals between the different registers and setting up flags. So that's if the register is going to be used, it sends a flag to the bus, and then it broadcasts to the other line that's the register is going to be used, so that it either stalls or performs an operation first, or whatever way they have to deal or to solve the hazard. So I'm just going to move on to the next one. Another graph showing the growth in clock rates of microprocessors. 15% per year, Y performance improved by 22%. 2%, blah, blah, blah. Yeah, whatever. So this is energy improvements, comparison of the energy and die area of arithmetic operations and energy costs of accesses through SRAM and DRAM. From Mark Holtz, Computing with Energy Problem. Interesting. Wafer, shoot types of risk there. Another table. So this is the execution time for different processors. 3 Dell per edge servers being measured by and their prices. This is showing the. I think that maybe I took 2 different pictures of the same graph. And this is just showing the memory hierarchy. So I have the registers on the CPU, then you have the L1, L2 cache, and L3 cache here, and the memory. And then the storage, which is the either flash memory, which I think is going to be SSD, or the disk, hard disk, which is a magnet disk. That's a lot slower to get the memory from, and that's why you create the register, the hierarchy, obviously. But this is a simplified version. So the next one is going to show the one that's, yeah, SSD, solid state first. The next one is going to show the more accurate thing, I think. So it seems that processors had a much higher improvement rate, and obviously I think it's because of the organization. So like I think the memory is more bounded by the physics of the transistors, the material, and the processors, they scale more because it's based on space and the organization of space. So I think because of all the logistics of the industry and the equipments, they like have exponential compounding improvements. It becomes easier to put more stuff on less space, and I think that's the reason why processors improve faster and can have like multiple different cores, and the other stuff that the algorithms make it easier to also design the hardware structure. So I think that's the reason why probably processors have had higher improvements in performance. Maybe I skipped the. Is that internal organization of a DRAM? Other DRAMs are organized in banks up to 16 for DDR4. Each bank consists of a series of rows sending an activate command, opens a bank and the row and loads the row into a row buffer. When the row is in the buffer, it can be transferred by successive column addresses at whatever the width of the DRAM is, typically 4, 8, or 16 bits in DDR4, or by specifying a block transfer and the starting address. The pre-charge command calls the bank and row and readies, not sure how to say this, it for a new access. Each command as well as block transfers are synchronized with a clock. See the next section discussing SDRAM. The row and column signal are sometimes called RAS and COS, based on the original names of the signals. So another table showing the capacity and access times. So basically the improvements by year. Clock rates, bandwidth, and names, blah blah. Power consumption, amounts. Next. Maybe I skipped the one that I'm thinking about. Let's see here. Did I skip this? No. Yeah, I think it's gonna be here. So associativity is as far as I understand now, is the way that they decide to design the addresses. So like all that an address is like a number that specify which row of the data it is. So you have several different rows, and then each row has a tag, and the tag would be the number of the row, and that's the address. So there's different strategies to, because you're gonna put on the hardware this logic of like how the bits are gonna be interpreted to create the logic of the relationship between the addresses. So obviously, like you can say that the top address would be the highest and the one in the bottom would be the lowest, or could do the other way around, or any other form you want. And I think that the choice of how to organize this relationship between addresses on the caches is called associativity. And obviously this matters because it's all related to space and time. So obviously based on the, maybe not so obvious, but like based on the laws of physics, time is always going to be connected to space, and you're always going to have this relationship between space and time. So it's very likely that operations that are done in one address are gonna be close to other addresses because it's based on the logic of the programs. And the programs are gonna be this way because it's just a consequence of the way the space-time works. Because if it wasn't this way, then geometry wouldn't be the way that it is. It's like, this is called cache locality. So obviously, based on this, I believe that's why and there is, I don't remember which one of the books or resources that I've seen, but I think that they use a module 2 strategy for the addresses. So they try to put the addresses that are closer to each other on the same cache. So the question is like, how do you make the distinction of when to create a different cache? And that's by following these formulas, I think. So, and it's based on how likely it is for an address to be used next to other addresses. So like if all the addresses were equally used, so like they were used on the same frequency, by definition that would mean that like space would have to be different. That makes sense for that to be the case. It's kind of hard to explain what I am thinking. It would mean that you have an infinite amount of possible states at the same time, which doesn't make sense. Like the only way for you to have time and space is if you have transition between states, and because you have transition between states, that's what creates space. So it's always this relationship, like at the boundary of space would be like the least likely thing to be used, let's say, which like that's the event horizon of space. And the more frequent something is, the closer it is to the observer. So that's the reason why there's always this link between how frequently something is going to be used and how much space it gets to access that, if that makes sense. So yeah, I'm almost 100% sure that this is the reason why things converge to, this is the reason why you don't have like the same amount, the same way, the same structure of memory, and like is this uniform thing, and you need to have this hierarchy. It's a natural convergence because it's a consequence of the way that the structure of space-time works, because it is a space-time itself. And again, I think that Ken Wheeler talks about this, but talks about it in a different way, which is based on the phi ratio. So the reason why it's a triangle is because of that, I think. Like, so like time is a hierarchy. Yeah, it has to be a hierarchy because it's a projection from the observer. So it follows phi, which is the frequency of transition of change in space. So the frequency of transition of space is what time is, which is a measure of scale. It's going to follow the golden ratio because that's how the geometry of the electromagnetic field works. And this creates a relative multifractal funnel of information, I think. So it's a hierarchy because that's the... But I'm obviously not 100% sure about this, but I do think it is like the perception of the observer, which is the perception of the observer is a projection, and because it is a projection, it's like a pyramid, and is on 3D as well as this because that's like fundamental to the way that space-time works, because it's just a hologram. So, and because it is three-dimensional, it's going to be a pyramid, but it's always relative and it's multifractal. So this creates a probability, distribution of probability that it is a hierarchy, and that's going to be the relationship between time and space that is going to create. And the difference in geometry is going to be on the difference of frequency of the fluctuation between the addresses, which is going to be the computation. Relative access times generally increase as cache size and sensitivity are increased. This data come from the data assume typical embedded SRAM technology, a single bank, 64 bytes blocks. The assumptions about cache layout and the complex trade-offs between interconnect delays. Interconnect is the logic gates that connect different banks. So you have like a bank is like can imagine like a square. Obviously, depending on what kind of device it is and how they create the memory, it's going to be a cube, just 3 dimensions. And Branch Education has a lot of very good videos about this, where they show like the 3-dimensional gate and how it works. But an easy way to think about it is just like a square. That would be a bank, and each row would be like an address. Each row has a tag, which is the address, and the value is the data. So the bits of that row is what the data is. And yeah, they're organizing these banks, and then what connects the banks is the interconnect logic gate structure. So it's kind of like a bus between the banks. Assumptions that depend on the size of the cache and the cost of tag checks and multiplexing lead to results that are occasionally surprising. Cache size is increased because search representation high technology, blah blah blah. Whatever. I'm gonna ask this ChatGPT what this one-way, two-way means, but I think it is based on the thing that I explained about the associativity. Organize and access. One way is SATA associativity. Each memory address is mapped to exactly one place in the cache. Can be stored in one of 2 possible blocks. Yeah, so it's basically this relationship between the addresses and the blocks. And that's gonna change, depending which one you select, is gonna change this trade-off between space and time on how the addresses are used, because obviously that's gonna be done. I think that it is both software and hardware, but it is embedded on the hardware, the structure to cache, but it is related to software as well. So there is the side channel attack, the Spectre side channel attack, is exactly because of this thing about cache. And the reason why these things happen is because the reason why hacks happen is because you have to make trade-offs in order to have performance. So the example of this is the Spectre, which is they use a reorder buffer and use a cache. So in order to make it faster to execute, the hardware is going to predict which branch is going to be taken, and then it's going to use this reorder buffer to keep the instructions in case the branch is not taken. So you can go back, or no, in case the instruction is taken, it's going to use the reorder buffer. So it's kind of executes the instructions in advance on the reorder buffer, and then and it puts them on the cache as it executes them. But then if the branch is not taken, it's gonna flush the instructions from the reorder buffer, but it's not gonna flush the cache. And the reason why is because of performance. Because if you flash the cache every time that you took the every time that the branches were not taken, then you would hit performance too much. So because of that, it's like a compromise that you have to do on the hardware, and that leaves you open to exploitation because of the time of the timing of the cache. Because obviously accessing addresses on the cache is going to be faster than accessing them on memory. So what they do is to create this like speculation on the hardware, the instructions to speculate on the hardware by passing memory addresses that they want to analyze on purpose in order to the hardware to flush the instructions, because it is like trying to access a place on the kernel that you can't have access to. But then it doesn't flush the cache. Then they run programs again and then they compare the times that it takes to access different addresses, and then based on that you can create a profile of the memory on the hardware. So like you're indirectly getting information based on the time that it takes. And yeah, they use least recently used on the hardware to keep track of what addresses are going to be on the cache or not. And it's based on flag bits and queues, I think. So the decision of which thing to put on the cache is done on the hardware for performance, I think. I'm pretty sure it is because of the translation locus buffer. So this is how many cycles you lose if you miss the cache. Whatever. Yeah. So this is the one that I was, and there I believe that actually there are more. This is the first one that is interesting, but it's very confusing. I'm not sure if I'm gonna spend time though. I think I was just gonna try to go faster because there's so much stuff to see. So the virtual address, physical, and data blocks for the ARM, Cortex, whatever, caches and TLBs, assuming 32-bit addresses. Top half A shows the instructions access, the bottom half B shows the data access, including L2, the TLB instruction or data. So this is something that is kind of confusing to me. Like, why would they get the instruction? Yeah, I think that it actually makes sense because, but I'm not really sure if it does though. Yeah, so I think it does make sense. I'm trying to think about how to ask this to ChatGPT, but like what is going to happen is that because of the instruction set architecture, there's going to be predefined bits that determine what each thing is going to do, and it's based on a MUX, I think, which is a multiplexer that has a selector signals. Those are the control signals that allows them to predefine what each bit is going to mean. So like, for example, if you have an add instruction, you can have add instruction, subtract. The difference between them would be what bits are set on this instruction register, or the instruction register that has the whole thing that I showed on some of the pictures ago. So this is the decoding process. So it's reading those bits that are responsible for the instruction. And I think that it kind of does make sense to have a cache for that, but it is kind of weird. So I assume that obviously it's probably based on how frequent those instructions are running. So like if you have for example, a loop on a vector and you're gonna add something inside of the loop, then obviously it makes sense to put the instruction on the cache instead of maybe like decoding through a longer path by using register. So yeah, I think that's the reason why you have two different caches. And the other one would be for data. What I want to ask ChatGPT. So on this book here, Understanding the Linux Kernel, they talk about on the appendix, I think, they talk about what happens, which I always wanted to know. What happens after you boot the computer? What are the stages? I think I wrote there, but I'm probably gonna look into this later when I'm going over the folder. So I'm gonna do this folder first, which has more hardware related stuff. Then I have another folder that has OS stuff, and then I have another folder that has network info stuff. So when I do the OS review, I'm going to go over these steps. But there's different modes on the hardware that are designed on the hardware that are based on the CR3 register. From what I remember, the CR like family of register is related to this transition between states, and the transition between states are pre-encoded on the hardware with combinational logic, and is a finite state machine. So it's a graph of different states you can have that is based on these registers. So it starts off, I think, on the real modes, which is like and the reason why I have modes is for the kernel rings and stuff. So like the more strict the mode, the less things you can do, I think. So start off on the base mode, which I think is the real mode, and on that, when it starts the hardware, on the BIOS starts the hardware, it doesn't have virtual addresses because a virtual address is an abstraction that is going to be done based on the operational system. So the operational system is the thing that creates the translation between virtual pages and the actual physical hardware. But when the computer starts, when it boots, the BIOS is gonna be loaded, which the BIOS is encoded. The BIOS is coded on combinational logic on a ROM, which is read-only memory, and it has predetermined logic of like it's gonna put the one address on memory on a predefined place. Then it's gonna initialize some other parts of the hardware. I don't remember very well the nuances, but then at some point it's gonna start the OS code, which is also gonna be on memory, because the main difference between what is considered to be code and what is considered to be data is just the instruction set architecture. So everything is data in the beginning. Actually, always everything is data, and the main difference is just how the BIOS and the hardware are gonna read the data. So before the OS boots, there is no. I think that segmentation. I'm not 100% sure if there is segmentation before, but I think it's mainly on the operating system. So the operating system is like a program, like any other program, and it creates these abstractions by using the CPU paths to create this the segmentation and the virtual addresses and the process abstraction. And the way that the operating system prevents a process from hijacking from running forever is based on timing. So the operating system schedules code, and then it has like predefined timing in order to stop processes, so they don't run forever. And all of this is based on interrupt registers that it sets. So, and this was one of the most confusing parts for me, but now it's like a lot more clear on my mind how it works. Like the only program that actually runs is the operational system. Every other program is actually the operating system that is running. So on the actual processor, on the hardware, the only thing that is running is the operational system, and the operational system creates an abstraction that allows it to run other programs. So when a program is running, it's actually running from the operational system, but yeah, so it's like the operational system creates the abstractions, and then it sets up this interrupt timer before it runs the process. And then if the process takes too long, the operational system stops based on the code that is set before, stops the process, and then takes control again, and saves the process information on registers like on these abstractions. So you can imagine that you have structs on C that are the code from the operating system, and those placed in memory are going to save the information for restarting the process. So it's always going back and forth, but the only thing that is always running is the operating system. All the other programs are like generic ways to run any code you want from the operating system. Yeah, so it's like a different thing. Is that this is the thing that I think I was confusing the decode with the fetch. So you have the fetch part of the process which happens before, which is getting like the instructions from like the program to run, and this is being done by translating from the virtual address, because the process always runs on the virtual addresses. So the process is just an abstraction that the operational system creates, and you can imagine that it's part of the code of the operational system to create the separation in memory. So it's like the operational system is like the manager that is allocating space on the hardware for the process, for the program that you created to run. So, and the way that it does this is by using these virtual addresses. So, and this is what ChatGPT is saying. Like from, in order for you to get the actual instruction from physical memory, from the virtual address that the operating system created for the process that is running, it's going to be slow. So that's why you need the cache to make it faster to retrieve the each instruction of the program that is running. Yeah, so this is basically showing the circuitry to translate a virtual address into a physical one through the caches. So this figure doesn't show the valid bits and protection bits for the caches and TLBs. So TLB is translation look aside buffer, and it keeps tags of the addresses. So according to this, you're gonna receive the virtual address here. So it splits off based on the page number and the offset. So offset is obviously gonna be where, so it's kind of like the same thing as a struct. So the page number would be the whole struct, and the variable inside of the struct would be an offset. I don't know if it's exactly the same thing, but it's like the same concept. So the page number is going to be the tag on the TLB, and then based on that, it's gonna get the real page number, and this is gonna be used on the L2, and the offset's gonna be on this L1 cache index and the block offsets. So I guess the tag here based on this, and if there is data, it goes to the CPU. So here imagine that if they are equal, that's a heat, so it goes to the CPU here. I think that's what's happening. And probably this is the reason why it's kind of confusing to see these circuits and understand exactly what is going on. Because obviously, it's not their fault, obviously. It's just that there's too much information. Should be, and the actual information is on the book. So obviously, I highly recommend reading all those books. I think probably watching videos is better, but like a lot of this stuff I only found on the books. I didn't see on the, except Honor Mutlu. I think is probably the best videos about this stuff. Yeah, but I think this is one of the best pictures that I've seen. This isn't the other one that I'm gonna go over. That shows the like this relationship between the virtual address and the physical one. So here is gonna be just the L1 cache. So if it doesn't find, it's gonna try to access the L2. Is on offsets. Yeah, so imagine that this is like kind of like a mux. So this would be selectors. So like if this doesn't, yeah, I'm not really sure though. That makes sense. Oh yeah, if no, yeah, I'm sure. 'Cause it is kind of confusing. No, I think that what how it works is based on the. So if it doesn't find here, it's gonna go over this path, and then it's gonna. No, that's if it finds. So if it finds, it goes here, and then goes to the CPU again, based on the offset from here. But if it doesn't find, then it's gonna go through here, and then this is gonna allow this one to work as well, the index. So like when this one is running, the one that it hits, is not gonna send anything here, which is gonna make this one do nothing because it's based on the logic gates that work based on this control elements, which is I think that the main one that I remember is the multiplexer. So multiplexer is basically some logic circuits. If I remember correctly, it's gonna be AND logic gates. So connect logic gates with AND, and then it allows you to put these signals that determine how the input's gonna transform into an output. So it's basically a function on the hardware level. Then based on this, it's gonna send here. So this would be the L2 address, which just comes from the physical of the other one. And same thing here, LB. It's basically the same logic, just another layer. Then here would be, I think either L3. Yeah, the main difference between the other one and this one is here. But I think it's kind of the same thing. Yeah, I don't understand what they mean by this arrow here. The virtual address, physical and data blocks for the RAM. Top half shows the instruction access, the bottom half B shows the data access. TOB instruction on our data. It's fully associative, each with 10 entries. On I cache or L cache. It's two-way associative, 64 bytes. Okay, blah blah blah. Sure, it doesn't show the valid bits. Yeah, let's go. Next one. Yeah, so this is an interesting formula. I think it's about the heat. No, no, the index. The formula for the index. First level caches are virtually indexed and physically tagged. Hmm. While the L2 and 3 caches are physically indexed. Some versions of this will support fourth level cache with the snaps of an access memory. First, the PC is sent to instruction cache. PC's program counter. The instruction cache index is, so this is the formula of the instruction cache index. It's cache size divided by block size times sets associativity. Access latency is how many cycles it takes to access, obviously. Characteristics, which has separate first level instruction. Obvious warrants, blah blah blah. And so I'm gonna go over the next one. Tree level cache hierarchy. So basically another one that's showing relationship between the levels, how many cycles it takes to access each one, and their associativity. Yeah, so this one is the one that is more complex, more detailed. Intel's i7 memory hierarchy and the steps in both instruction and data access. Only writes are similar except that misses are handled by simply placing the data in the right buffer because the L1 cache is not write allocated. Writes are similar except the misses are handled by simply placing the data in the right buffer. The L1 cache is not write allocated. Not sure what they mean by this. What does it mean for L1 should not be right allocated? I think it means that it doesn't allocate if it misses. No, it doesn't allocate writes in the cache. It's probably what it means. So L1 is only for read instructions. Yeah, I think that's what it means. So here you have the instruction and then I have the data part. This one is very complicated, as you can see here. This would be the translation look aside buffer. Then L2 translation look aside buffer. Cache. So maybe the data is, I spent some time on this one. Data is probably, might be easier to understand. So this will be the virtual page for the data and the offsets. So yeah, it does use a mux here to select. Physical address, thanks. This is gonna go. So this go from here and then goes here and here. So if it goes here. So this index also is received from the address directly as well. Offsets. I think it just goes back to here if it hits. So if it hits, the mux are gonna give the output should go here, I think. Just like go back and this is like the outputs here. Yeah, that has to be the case. Then if it doesn't hit, it's gonna go on the other mux and then continues the flow from there. It is very confusing though. Yeah, and this would be the main memory, so if it doesn't hit anything against from the main memory, it's gonna be the DRAM, I think. Then if it doesn't get from the main memory, it gets from the disk. It's a lot slower. I think I'm just gonna go over the other ones, so otherwise I'm gonna spend too much time here. Obviously, I get it, like you can just follow each thing here to see like where you would go, and then depending where you would go, you would change the state of the monks, which you would change the path whether or not he goes from the other to the other places. And I assume that this is gonna be like this line here is connected to these other ones. Not sure though. Yeah, so I'm gonna move on to the other pictures. I spent too much time. But the easiest way to without understanding everything on the circuits, like the concepts are a lot easier to understand. It's just a hierarchy of translation look-aside buffers, which cache the tags of the either the instruction or the data. Then if you can't find with the translation performs like the name says the translation. So based on the tag, it finds the page and then it looks for the page on the cache. Then if it doesn't find another cache, it goes to the other uh, TLB and then the other cache until it reaches the main memory. And this so one of the craziest things is like how the fuck do they like it's so insanely complex. It's crazy how like people were able to do this in the first place. Okay, because like it's obviously gonna be billions of transistors. So one of the main things that is very confusing to me is like how do they if it's multiple different companies working on different pieces of the hardware, how obviously it's based on standards and it's gonna be based on buses to connect the different parts of the components. But it's so uh, on the actual physical thing, like how do they make sure that everything's gonna connect with everything else? And how does that even work on the in practice? Like so crazy that it works. Because if you think about it, everything is dependent on the synchronization of the clock cycle, and Honor will also like explain that a lot of the times what they have to do is to split the output of one clock into several other ones in order to make sure that the time is going to work, because obviously it depends on the structure of the logic gates. So if you only have one clock, then it becomes, I think, probably impossible to synchronize, because like the one company is gonna create the clock and then the other company is gonna create the other logic system. So like, how do we make sure that the longer path of the circuit is gonna match the frequency of the clocks so that you're able to set the state at the correct time. And the way they do this is by like changing the or connecting more clocks, and then you synchronize on the other clocks. So the output of one clock becomes the output of other clocks, and basically is this function of the synchronicity of the frequency of the clock with the longest path and longest and shortest path of the circuit. So on this one specifically, the instruction fetch stuff is here. Memory controller, teacher mapping, instruction cache. Yeah, so this is a branch prediction circuit, I think. Yeah, G-share predictor with 1024 entries, which being standard 2-bit predictor. So from what I remember, the 2-bit predictor is gonna be like just a simple. It's gonna wait for 2 misses in order to change the state, as far as I remember. Like 1-bit predictor would be like, let's say you always predict that the branch for the address 1000 is going to be taken, and then it's not taken, then you stop predicting that address and you change to another one. So let's say you're expecting 1000 and then you get 2000, you would immediately switch to 2000. But I think on the 2 bit, you just change for the first time you encounter the change on address, which you change for, you might be 2000 instead of 1000. And then the second time you see at 2000, then you change. And I think that this prevents like on loops after like it goes in and out of the loop, so that it doesn't change as often. It's just more efficient than the more simple one. But now obviously using machine learning and other stuff more advanced, which is probably the conversions of the tractor state of where everything is gonna go. Just more complex because obviously you can look based on data, and then you have hardware that's gonna be optimized, and you're gonna do operations on the memory, which is ping, the processing memory. And that's I think the natural conversions of these things. So like the states of the execution is gonna be linked to the density of memory. So the probability of the past dictates the efficiency of the future. Because it is a cycle. So apparently it works with the exclusive OR, XOR. Branch history, global predictors. Determine predictor using the branch address to index a set of 2-bit selection counters. We choose between a local and a global predictor. In this case, so I think that this is for when you have multiple processors, maybe. So you have a global one that keeps track of all of them, and then you have a local for each one. And then you do based on both of them to predict. So basically the same pattern, but more complex, like an extra layer of abstraction. Five components tagged hybrid predictor has 5 separate prediction tables indexed by hash of the branch address and a segment of a recent branch history of length 04 labeled H. Hash can be as simple as an exclusive OR as in G-share. Each predictor is a 2-bit or possibly 3-bit predictor. Tags are typically 4 or 8 bits. Then chosen prediction is the one with the longest history, where the tags also matched. And so this would be like a very simplified, kind of like machine learning way as well. It's not really because it doesn't change, but yeah, it would be like very similar because the longest one would be the one with the highest weight, but it's a very simplified version, I think. Of that thing, and uses XORs to get the inputs. This prediction rate for integer benchmarks. The basic structure of a RISC-V floating point unit using Tomasulo's algorithm. I wrote down this, I think, on the spreadsheets there of the review stuff. Instructions are sent from the instruction unit into the instruction queue from which they are issued in first in, first out, so basically queue. The reservation stations include the operation on the actual operands as well as information used for detecting and resolving hazards. Load buffers have three functions: hold the components of the effective address until it's computed, track outstanding loads that are waiting on the memory, and hold the results of complete loads that are waiting for the CDB. Similarly, store buffers have three functions: hold the components of the effective address until it is computed, hold the destination memory addresses of outstanding stores that are waiting for the data value to store, and hold the address and value to store until the memory's unit is available. All results from either the FP units or the loads units are put on the CDB, which goes to the FP register register file as well as to reservation stations and store buffers. Adders, implement addition, subtraction, FP multipliers, the multiplication and division. So I have instruction units here, load operations here, loading points, operations, operation bus, reservation station, common bus. I'm pretty sure that I wrote this stuff here. Yeah, Tomasulo's algorithm, hazard dependencies algorithm. This is related to hazard dependencies. I think maybe it's not, but that's what I wrote there. So I think probably is. However, so this is related to reordering buffers, so speculative execution probably. Basic organization of a multiple issue processor with speculation. In this case, the organization could allow FP multiply, FP add, integer, and load store to all issues simultaneously, assuming one issue per clock per functional unit. Note that several data paths must be winded to support multiple issues. The CDB common data bus, the operands buses, and critically, the instruction initial logic, which is not shown in this figure. But this is a difficult problem as we discussed in the text. And so I think this is the unit that executes the speculative operations. And it executes multiple instructions at a time, I think, probably. Instruction unit here. So I think that this is the first step on the circuit. You have this queue of the instructions, and then it allows floating points and load and store operations. So this reservation. So yeah, from what I remember from ChatGPT responses, the reservation stations are used for solving the hazards. So it works based on a broadcast, I think, or something like that. Where like if there is a instruction that is supposed to execute before another one, but it is not that way because it's trying to execute multiple at a time. I think it sends a signal on the bus, and based on the signal and this reservation station, it either waits or discards the or something like that, or does the operation first or something like that. I don't remember the details very well. I have to review this part a lot more. It's kind of hard to find like a lot of information, I think. Maybe it's not that it's hard to find the information, it's just that there's so much stuff to learn. It's hard to focus on only one thing at a time. But I think what I'm gonna do is just as I review on the concepts there on the spreadsheet, I'm gonna use ChatGPT to get like a superficial sense, and then I'm gonna look for other resources to reinforce. But I think that's what's happening. So the reservation stations are maybe I should ask right now. Don't remember which. I think it's this one. I'm gonna click on this one. It's probably this one that I was asking about hazards. Yeah, here. So next one. Number of entries in branch target buffer. A branch target buffer, the PC of the instruction being fetched is matched against the set of instruction addresses stored on the first column. Addresses of known branches. If the PC matches one of these entries, then the instruction being fetched is a taken branch. Predicted PC contains the prediction of for the next PC after the branch. So I think that the spaces where there is the most nuance and complexity is going to be on the data, obviously, and on the branch, which is always the main fundamental things. But I'm not really sure which one is. I think that the actual memory is more complex, and the registers. So I think that most of the complexity of the register data is on the hardware. So dealing with the like these optimizations of registers is done on the hardware, I would assume. But also there are a lot of optimizations on the compiler as well that I remember. And I think the memory optimizations are a lot more complex. So they're probably more on the software. I think that's the range of the polarity. But both of them open up space for exploitation because it's just a natural trade-off of I think it's a fundamental property of the universe. I was talking about this with ChatGPT as well because it is a polarity. So like if you have full privacy, then you have full security, but then you don't have space-time because there is no transaction, there's no transition between states. But the moment you don't have full privacy, then you open up yourself to exploitation. And I think it's basically the same thing with hardware and software. At the moment you need to open up some vulnerability spaces in order to optimize the execution, and that's a natural attractor state. But the moment you do that, then it opens up vulnerability, and I think that's the flow of information. So the complexity is always gonna increase on the range of that polarity. So this is just a finite state machine, I think, or some logic flow graph showing branch decisions. However, prediction accuracy for return address buffer operated as a stack on a number of spec, whatever. Return address predicted correctly. Blah. All four different approaches use the functional unit execution slots of a superscalar processor. Horizontal dimension represents the instruction execution capability in each clock cycle. The vertical dimension represents a sequence of clock cycles. An empty white box indicates that the corresponding execution slot is unused in the clock cycle. The shades of gray and black correspond to four different threads in the multithreading processor. Black is also used to indicate the occupied issue slots in the case of the superscalar without multithreading support. Processor fine-grained multithreaded processors, whether Intel Core i7, blah blah, has 8 threads. Issue from the thread at a time. So I think what they are calling thread here is the different lines of execution. So each line is like a sequence of the execution cycle. And yeah, the amount of lines you have is the amount of threads you have on that data path, which is the processor or the CPU. So I'm gonna read the ChatGPT stuff here. I think I'm gonna go back to the other chat here. Yeah, so this is, so I did remember correctly. So the primary role is to prevent hazards on out of order execution. So the hardware dynamically or hardware automatically reorders the instructions in order to optimize how many instructions are done per clock cycle. So like if you have on the code, I think the compiler does that as well, but if let's say you have on the final assembly code or on the final machine code that ABC is gonna happen, the hardware might do CBA or any other order based on so I'll try to do the most amount of instructions as possible on each cycle. But the moments where you can do that is when there is like a dependency. So it's like a cause and effect relationship. And on these moments it's called a hazard, and that's why they use this reservation station. So like they connect the circuits with buses, and I think that the way it works is based on broadcast. So I think yeah, the way that it works probably like if an instruction uses the register 1, for example, it broadcasts on the bus to for the other places that would execute. They are gonna execute the same. Are gonna execute instructions at the same time. They know that the R1 register is being used because it was broadcasted by the first thread. So if another instruction would depend on the R1 as well, then instead of executing right away, it does something else. So, and I think that's what the reservation stations do. They achieve this by holding dependent instructions until their operands are ready. Yeah, so that's the thing. Rather than installing the entire pipeline. Just kind of like a buffer. So if there is a dependency, it holds the instructions of the buffer, which is the reservation station. But if there isn't a dependency, then the multiple instructions are executed right away, out of order. Yeah, so when the required operand becomes available, it is broadcasted via the common data bus. So what it tries to do is to use the register, but it sees that's being used by the other instruction. So it puts the instruction on the reservation station. Then when that instruction is finished executing, it's gonna send a signal on the bus, and that signal is connected to the reservation station, and then it's gonna allow to execute the other one. However, we're gonna read the rest. It's basically the same. So this instruction or this control hazard is based on the branches. So like when you reorder the instructions, then obviously if you are executing instructions that are not going to be taken because it's a different branch, then you have this problem that you execute something that it wasn't supposed to happen. So that's the point of the reorder buffer. It ensures that the instructions are going to be committed on the right order. So even though that they are executed on out of order, they are committed on in order. And this is why is speculative execution, I think. Like you're executing out of order speculatively. Then if turns out that it wasn't the case, it probably flushes the instructions, sends a signal to interrupt or something like that. Or to send a signal to continue for the official pipeline, let's say, to execute from the last point, which with the correct branch. This was a lot of other stuff. And so I think that is too much stuff to remember at what point I asked about these things. I'm just gonna continue. I'm pretty sure that this is the case, but I'm probably gonna look for videos later. I'm gonna continue. So this is the overall, um, like the concept, showing the concept of the execution. So F1 and F2 is the fetch. D1 and D2 decode. It starts here. And it's kind of weird though, the way that they did this. Maybe it's, oh. Yeah, I think, no, it has to be these ones. I think it fetches from here. Instruction fetch. And this is the from the right back. So I think it starts off here. So instruction fetch. Then it goes through the TOB. Then here it goes through predictor, indirect predictor, and decodes. Yeah, and here it executes. I think this one is just showing this in more depth. And then the right back would be going back and closing the cycle. Yeah, complete the integer pipeline. Because some more complex instructions overlapped. The first stages of execution. ISS. After I assess the so here, after here. Execution 1, execution 2, and write back stages, complete the integer pipeline. Benches use 4 different predictors depending on the type. The floating point execution pipeline is 5 cycles deep. So I'm gonna go back or move on to the other ones. Is the Intel Core i7 pipeline structure. Total pipeline depth is 14 stages with bench predictions typically costing 17 cycles, with the extra few cycles likely due to the time to reset the branch predictor. Function unit, begin execution, blah blah blah. So obviously, I think that starts here. Instruction cache goes to the TLB here. Decodes here, instruction queue. As I think it tries the cache here. So if it hits the cache, probably goes first, I think. Not really sure though. Then it has this decoders, or the bus here. It rear the buffer. Reservation, then executes. Yeah, X. And X. One of the most confusing things is the stuff about segments. I think that on a linear address model, segments are also used. So like, segments are on registers, I think, and they are used by the operational system to organize the virtual addresses. But it's very confusing. I think it's because I've seen like the thing is I'm not really sure if there are contradictions because it might be a different context in the way that the person meant. But I have to remember. Hopefully, at some point, I am 100%, not 100%, but very confident that there is some images here or some content related to register or to segments. So the register renaming table. So this rename is for, I think it's for hazards as well. So like it allows you to run a bunch of instructions without going through the hazards because it opens up more registers. Like something like that. And there's also some stuff that the compiler does that is related to this as well. Yeah, I think it's kind of like creating a temporary variable so that you don't mess up the value of the other one. So if I have two instructions that use the R1 register, what you can do is create a table that maps that R1 to a unique name. So R1 becomes X and on one instruction, and R1 becomes Y in the other instruction. Then when it gets time to execute the instructions, you like update the table with the values for X and Y. So even though they're using the same register, you are changing different values, and then it allows you to execute more. Yeah, from what I remember is something like this. And I think it is on the hardware as well. But I know that the compiler, so on the compiler, I think is called single static assignment. Yeah, I'm pretty sure it's single static assignment. That the compiler also does this in order to optimize the instructions. Yeah, basically the instructions, the way that the code is gonna work, because the compiler changes the code that it was written, and it in order to optimize how it's gonna execute for each architecture. So the way that the compiler works is that they break down everything on the control flow blocks, which becomes a graph. So it's a control flow graph. And then based on that, because each block is viewed as its own like unit, let's say, you have this you can have different conflicts depending on which branch is taken. You can have the different variables based on the way that they organize the variables because they use this static single assignment form. But I don't remember really well, like the nuances of this. Yeah, but I think that they do it like this to also reorder instructions or to move them out of the loop or yeah, stuff like this. But then when you do this, then you have this conflicts when there is a branch. So or like when two different blocks converge and you have the same variable, like you previously was the same variable, but then because you renamed the variables, it becomes two different variables. How do you decide which one is gonna be the like real one? And then there's some like complication or yeah. The name is static single assignment of this stuff. There's a, I'm gonna see if I can find, I should probably watch that again. It's one of the best courses I saw on compilers. I don't remember from, there is a, like the official channel is not on YouTube, but there is a playlist on YouTube from the course. But I remember it's from somewhere else. It's like it's from a college. I think it's Cornell or something like this. I think it's Cornell Advanced Compilers. Oh, I found. Yeah, Cornell CS 600, 6,210. I might watch this again actually. It's a very good course. But it might be better to like do stuff with LLVM. I think he uses a LLVM on this, and he also uses another language, I think, to explain these concepts. But he talks about this stuff on this lecture here, static single assignment, of the renaming the variables. So there's both the data flow graph, which is a graph of the data dependencies, and then there is the control flow graph, which is the graph of the branches. And they're both used to optimize the instructions and to reorder instructions. It's like basically the same pattern and on the hardware and on the uh, compiler. And the main reason why you have on both is because of the trade-off. So obviously it's cheaper to do stuff on the compiler because you don't have to spend more money on the actual circuitry. But then obviously you have to do more work on the compiler. This will be for GPU, I think. A single instruction, multiple data. This is a GPU pipeline. Have a thread scheduler. Block diagram of multi-threaded SIMD processor of a Pascal GPU. Has pipeline floating points units, a pipeline integer units, some logic for dispatching. Yeah, whatever. It's also a GPU, vector processor for lanes. I'm gonna try to go faster so I can look into more stuff. This is connecting memory. Basic architecture of a distributed memory with processor. And possibly I/O, chain interconnection network that connects all the nodes. Write and validate cache coherence protocol for a private write-back cache showing the states and state transition for each block in the cache. Yeah, so basically the way that the cache coherence works is based on a finite state machine. So finite state machine is hard-coded on the hardware to determine what's going to happen depending on which state that address on the cache is at. And then it allows you to make sure that the different blocks have a consistent or coherent memory model. So like one of I've seen the two main ones that I've seen is the snooping protocol and the other one is the directory protocol. So snooping is the cache broadcasts on the bus to the other blocks what happened with the address. So if it's a read, invalidate, or write. Or basically these different options that you have here that make the states transition to another state. So invalid shared, or there's a name that I forgot. There's an acronym for this. But the other coherency protocol is that you have one block that you assign as the directory. So it's like the one that is responsible for synchronizing all of the other ones. So instead of broadcasting to the bus, the blocks send the signal to the directory block. And then that block's gonna make sure that it synchronizes based on the finite state machine as well. She determines the transition between states. And it seems that the directory one is more efficient. And I think this also has to do because of the laws of physics and because of the structure of space and time. Because if you think about it, the directory model creates a hierarchy. So it's like that pattern of the pyramid, which I think is a kind of fundamental thing about space time. It's a natural convergence towards that. I think it's forgot which one. I think it's MSI. I think it's MSI. So modify, share, invalidate. Something like that. The acronym. So if you have a memory that it's only this state and then you read, then it goes to this other one. Just shared, read only. So if you read, it keeps here. If you read and miss, it keeps here. If you write, then it goes to the exclusive, read and write. And then here is write or read, keeps here. Write, miss. And the way that the arrows work on the hardware is just based on the control logic. Like have different signal, different lines that connect one circuitry with the other. And then they are based on this selection, based on the multiplexers. It's probably either multiplexer or decoder or encoder, the main circuits that are used to do this kind of logic where it allows you to like hard code transitions of states. And because like obviously the it has to be closed, the arrows, so it doesn't matter which state the hardware is at, it's always gonna like be has to be it's gonna be predetermined which one it goes. So obviously there's an infinite amount of ways to go from one state to the other. But because of the logic of the control, it's always gonna work. Another thing that I'm not 100% sure now, I'm gonna clarify more, but it was more confusing to me before, is this relationship between like the different parts of the system, especially when it comes to peripherals and other stuff like that. And it works on two different ways. Like there's two different fundamental things. One is the drivers, and the other one is the like this communication between the different parts of memory. So everything works based on buses, and the buses are based on standards. So that's why it's called USB, Universal Serial Bus. So like the bus are the lines on the hardware that allow for uh, the thing to communicate with the other parts of the system. And I think that the way that it works on each parts of memory that you have on the system, the connection between them is going to be done through something that they call ports. So a port would be like it's like a door on a house. So each line that connects that piece of memory with the bus is called a port. This part I'm not 100% sure about the like exact way, but on the concept level, I'm pretty sure that it works like this. And then the communication of them is done through these queues, I think. But there was some stuff that I remember that I read that like talked about the what happens exactly on that part. But I don't remember really well where I found this. And the other key components is the driver, because the driver is gonna be like the code that the person that wants to add the device to the architecture, they're gonna create a program that's gonna be run by the operational system, and uh, based on the logic of their program, is gonna allow the device that they created, or yeah, the device that they created to interact with the main component, so the main hardware structure. And the points of connection is where you have the standards. So the internet works like this as well. It works based on a network interface card, which is another hardware component that is connected with the motherboard through these ports. So when you receive a signal from the internet, you actually receive, so the signal comes from the cable, which goes from the modem. The modem translates the analog signal into digital signals using the amplifiers and the stuff that they talked about on the other book. Then from that digital signal is sent to the network interface card, and the network interface card has like predetermined logic on the card that is going to put the data on queues, and then the card is going to communicate with the operational system through the buses, and it works based on abstractions and interrupts. So when the network interface card receives a signal, it's going to generate an interrupt request for the main hardware. And because the operational system is the only thing that actually runs on the hardware, it's going to be the thing that the hardware notifies. So it's like it synchronizes everything based on interrupts, the external impulses from the main processes that are being run by the operational system on the actual hardware. But I have to study a lot more on this, like the nuances of the how the memory parts are connected with each other. Because I think that's it's probably always through queues. So, but it's very like these parts are very confusing because they're complex, and then there's several different architectures that are gonna have trade-offs on optimizations on because depending on which topology you choose to connect the circuits, you're gonna have different latency and bandwidth of the data traveling on the circuit. And one of the most confusing things is like what happens when you like because eventually the queue is gonna be full, obviously, so you can't send data forever. But then there's both that and there's to prevent the denial of service attacks. And the way that they deal with this is by first, like the operating system is gonna have this scheduler, which is gonna like be the manager that determines based on timing what processes run and like how much time is gonna allocate for the interrupts that come from the network interface card. So based on this, it's gonna like consume the data from the interface cards and it's gonna put the data on the memory of the hardware. But this part, I think that there's also nuance because the operating system is gonna implement the proxies and firewalls and stuff like that. But eventually, I think he's gonna send the data to, he's gonna make the process that is expecting that data receive the data, and then the process is gonna have logic to put the data or to decide what's gonna happen with the data, depending on the code. But for the packets that are, so if the queue is full and is still receiving packets, I think he's gonna drop the packets. And based on the protocol, there is like it's also based on timing. So if one of the sides sends a signal to the other one and it doesn't receive any response in some time, then depending on what state the connection is at, is either gonna drop the connection or send the signal again. And this is basically what the protocols do. But I'm still kind of like a lot of stuff to clarify when it comes to the drivers and the memory parts. But this is the point of the interconnection networks. So when on the lectures that Honor Mutlu talks about the interconnection networks, is also the same kind of hardware that is used to translate network data, data that's come from the network into the hardware. So it goes from one process on the server or on some other computer, then it goes through they call data link, but it's gonna go from the process running to the network card on one computer to the wire. Then it's gonna arrive on the other side on the modem. Then it's gonna go to the network card as well. Then the operating system is gonna receive that and is gonna send that to the process, to a process as well running. If it doesn't have any process, then it drops the data it doesn't accept. And if the there's also another stage that the network interface card is gonna drop the packets as well automatically without passing through the operating system. I think if the packet is wrong, if there's something wrong with the sequence of the frame that it sends, then the network interface card has pre-programmed logic on it. So yeah, it's gonna drop the packets. Routers are basically hardware components that keep tables of the connections, and then when it receives a signal, it checks on the table. So it's basically a bunch of hash maps connected through a linked list. That's how it works. So each router is like a hash map. Is either one hash map or two hash maps, depending on what position it is on the network. If it's a local network, it's gonna change, and if it's a like bigger network, then like maybe there's more hash maps to make all the connections. But it's basically hash maps that the router is gonna have, and then it's gonna be connected to the other routers. So it works kind of like a linked list of hash maps to send the signal from one thing to the other, and everything is like pre-programmed on the actual hardware using the uh, either read-only memory or EPROMs, erasable. What the other E stands for? Is EPROM? I think it's electronic erasable readable or programmable readable only memory. Yeah. So this is I'm not really sure how like when I took a picture, but I think it's related to machine learning. It's probably some stuff on the GPU related to machine learning or something. As ReLU, I'm pretty sure that yeah, ReLU, I'm 100% sure it is one of the functions that is used on machine learning. It's just the linear function for the. It's not the error function. It's for the for finding the local minimum or maximum. So the gradient descent, I think, function. Yeah, talking about. So it's convolutional. It's probably talking about the hard-coded networks on the hardware and hard-coded on hardware for convolutional neural networks on a GPU probably. So machine learning on the GPU or on FPGA. Yeah, we're just gonna go over. TPU block diagram. File buffer local systolic data setup. Yeah, FPGA here. And this is talking about compilers. So this is the formula for cache, average memory access time. Read time plus miss rate times miss penalty. So CPU address, block address. Like this is a simplified version of the other circuits there. I think it's kind of confusing, but I think that the segments are on the hardware is like it's registers basically on the hardware that allow the operational system to separate the memory for each process based on what they are. So I have the segment for the code, the data, and the heap and the stack. Then based on these segments, you can use the registers to access the memory in the hardware. So I think that's the reason why it's kind of confusing. So like the process part, the virtual addresses on the process are based on the segments, which is controlled by the register. The operational system uses the bits on the register to determine what part of the segment the address is from. Then from that part, it uses that to the hardware is going to use that segment, the bit set on the register, the segment register, to translate the virtual address into the physical one by going through that path of the translation local site buffer and the caches until it gets to the main memory and to disk. I think parts of what makes it confusing is that like each resource talks about a specific thing, and I couldn't find. Maybe I did find, but don't remember. But from what I remember, I didn't find any resource that talks about everything at the same time. So like the segments and the caches and the cache coherence and like everything. I think the reason why is probably because it's too much stuff to put on like one video. But like it's probably because there are differences in architectures. It's like this, for example, is kind of confusing because like here is obvious that it's saying like this is going to be used to translate the virtual into the physical one based on this like four levels here. But then like how is this related to the other stuff that I saw on the other one? Because you can imagine that there could be a lot of variance on like where you put like theoretically I think that there could be like caches on each part, but maybe not because they all depend on each other. So maybe like the caching stuff is after this, after you do the interaction, but then not sure if that makes sense. Let's see what it stands here. So this is the formula I was remembering about associativity. Key design decision is where blocks or lines can be placed in a cache. The most popular scheme is set associativity. Associativity. No, associative. The most popular scheme is set associative, where a set is a group of blocks in the cache. A set is a group of blocks in the cache. A block is first mapped onto a set, and then the block can be placed anywhere within that set. A block is first mapped onto a set, and then the block can be placed. Yeah, so it's basically because the cache is going to be a smaller version of the block. I think that's what it's saying. So you map the block to the set. I imagine that the set's going to be smaller. No, a set is a group of blocks in the cache. So how does that work? First mapped onto a set, and then the block can be placed anywhere within the set. Find a block consists of first mapping the block address to the set, and then searching the set, usually in parallel, to find the block. The set is chosen by the address of the data. I'm not sure if that's like very clear still, this explanation. Also, the block's not referring to the bank. I think I'm confusing things. So a set would be lines on the cache. A set is a group of blocks in the cache, so a group of lines. It's first mapped onto a set. So a set is bigger, and the block is mapped to a set. The block can be placed anywhere within that set. Finding a block consists of first mapping the block address to the set, and then searching the set. So I think I understand. You're just saying block has several lines, then those several lines are going to be like you're grouping similar addresses onto this block, which is just several lines on the cache. And the cache has a set which has several of these blocks. It's kind of like a neighborhood where the block would be like not sure how to say that in English, but the close buildings. Each block would be a building, and the neighborhood is the set. Yeah, that's probably a good analogy. So finding the block consists of first mapping the block address to a set. So it's finding the building on the neighborhood, and then searching the set, usually in parallel, to find the block. So it maps the block to the block address to the set, then search the set to find the block. This part here is kind of confusing. The set is chosen by the address of the data. So block address, mod number of sets in cache. So this is just a picture of a pipelined processor. So each line is like the lines of the instruction, the cycle of the instructions, and then it allows you to execute multiple of them at the same time. And the hazards, to solve the hazards, would be like connections, the control flow connections, connecting different parts of this. So think an example that I've seen, I think on one of the books, like a line connecting this register to this one or something like that. Yeah, so yeah, it is on this book. So these lines here would be like to solve the hazards. Let's see, go back here. The use of the results of the add instruction in the next three instructions causes a hazard because the register is not written until after those instructions read it. So that's because of the R1 here. Yeah, so it's saying, so here's gonna add. Yeah, so it's saying that the result of this one is gonna affect the other ones. So if this one executes first, is a problem because it's using R1. So like the moment that this executes, it's gonna execute with the wrong value of R1 because this one doesn't execute yet. So what you do is connect them through a control line. So the moment that this one is gonna execute, it's gonna broadcast, I think. And then depending what design choice you have, it's gonna do something else instead of executing. Uses forwarding path to avoid the data hazard. Yeah, so this one is basically sending the results of the operation directly into the other AOU through a control line instead of waiting to put their result on the register that this line here would use. So is able to do this because the instruction is done before it writes to the register. So obviously, if this line here happened before, then you wouldn't be able to send the result because the operation wouldn't happen yet. Wouldn't have happened. And so I think this one it talks about this, and then the way you solve these situations where like the only way to you can't forward because of the structure of the relationship between the lines is that you stall. So create fake operations, I think. The load instruction can bypass its result through the end and or instructions, not the sub, because that would mean forwarding the result in a negative sign. Yeah. Yeah, so here is only capable of loading on this part of the stage, and this is gonna happen after this already happened. But it doesn't. I think that I don't remember obviously what is said on the book. Yeah, but yeah, pretty sure that it just installs the operation. A branch causes a one cycle stall in the 5-stage pipeline. The instruction after the branch is fetched. So I think it waits on the branch that is connected. It's like it waits here, I think. Yeah, so normally I think that it does a cycle here. So based on yeah, but then how does it know? I think that this is a control line that is linked to the register here. So if this instruction is based on the register, it's going to be based on a mux. So Based on the selection, it's gonna know that it has to send the signal here. And then because it sends the signal, it does the loop instead of executing the instruction. So the moment that it executes is only gonna be after this one executes. Probably that's how it works. So this I think that yeah, this is the plot. The graph of the finite state machine of a 2-bit prediction scheme. So it basically goes like it changes the state based on whether or not it was taken. So like instead of switching right away, it waits one round. So the first miss, it goes from this point to this. So it's still predicting the same, I think. Then if it's not taken again, then it changes. Yeah. And then it's the same thing to switch to the other ones. Trying to go faster to see if I can finish this. The C18. Oh, there's too much stuff. I think I'm gonna finish this off stream. I'm gonna go quickly, or I'm gonna take a break now and then go over. I don't want to stop on the middle because I don't want to create another folder inside of this one to put the revealed ones. Just want to send the entire folder to the revealed here. I think I'm gonna do like this. Every time that I review this, I'm gonna do like folder by folder. So once I start a folder, I'm gonna do to the end. And it's probably just variations of the same stuff. The other books, I think that I have last pictures. I took last pictures. Yeah, so this is like the how you implement. I think this is like how you implement superscalar. Just create these additional steps here. The pipeline. I confuse the names, but like how you implement the lines there that he was talking before on the hazards. You do it through this stuff here. Data paths pipelines by adding a set of registers, one between each pair of pipe stages. The registers serve to convey values and control information from one stage to the next. Can also think of the PC as a pipeline register, which sits before the IF stage of the pipeline, leading to one pipeline register for each pipe stage. Recall that the PC is an edge-triggered register written at the end of the clock cycle. Hence, there is no race condition in writing the PC. The selection multiplexer for the PC has been moved so that the PC is written in exactly one stage, IF, instruction fetch. If we didn't move it, there would be a conflict when a branch occurred, because two instructions would try to write different values into the PC. Most of the data paths flow from left to right, which is from earlier in time to later. The paths flowing from right to left, which carry the register write back information and PC information on a branch, introduce complication into our power line. Yeah, so this is the write back. So all the computer is doing is going through this cycle uh, through an infinite amount of time until like it has the voltage to keep the clock frequency going. That changes the states, and it changes the state of memory by doing this. Like the computer is a memory changing machine, and the memory is just the geometry of the SR latches and the more complicated variations of SR latches. So the D flip flop, which is the or the master slave flip flop, which is just more complicated versions of SR latch that are based on control logic and the clock cycle as well. So it's just changing the pressure mediation of the ether based on the voltage, which is consequence of the capacitancy of the clock. And that creates the fluctuation of pixels that changes the information on the screen. I think this is a fundamental principle as well. Every time that you have these situations where you're going to have optimizations, I think that usually what's going to happen is that you're going to have this where you create another circuitry, like you create logic circuits that connect different parts of the components that are specialized in doing different things. So the memory case would be the interconnection network, and here would be like these networks here, and they are basically just going to be control logic that allows like more optimization for the flow of signals between the specialized parts. I'm just gonna skip this stuff. It's not gonna be. So this is like the operation that changes the program counter. So automatically by default, it's gonna increase the program counter by 4. I think it is by 4. No, I don't remember like if it's 4 bytes. I think it's 4 bytes on 32 bits. Because yeah, 32 is 4 bytes. So it's probably 4 bytes on 32-bit architectures and 8 bytes on 64. Because just moving a row, uh, each instruction, if you don't have a jump. If you have a jump, then it's going to be based on the jump, which is based on the add here. Then it goes back here and goes through the mux. So yeah, by default, it is 4. So it's 4 bytes because this is for 32-bit architecture. So it's 32 bits because each row of the memory is going to be 32. And I think that's the size of the register as well. So yeah, the size of the register is going to be 32. And then on 64 bits is going to be 8 bytes. It's probably going to be 8 on 64 bits here. So it just moves the program counter to the next row. And if you have a jump, it's going to change the value here. So it's going to jump to that address. PC can be thought of as a pipeline register as part of IDIF, so the code fetch, which is written with the address of the next instruction at the end of each IF cycle. So the difference between exception and trap is that exception happens within the process. So the process raises an exception when there is something wrong, when something went wrong on the process. And a trap is when there's a interrupt from outside of the process. And the trap is usually going to be, I think it is always based on the OS. So for example, let's say you have a mouse, you move the mouse or press a key on the keyboard and the process is running. The OS is going to trap the process, is going to store the state of the registers and everything like inside of an abstraction, which is going to be handled by the operating system. So it's going to put this stuff on memory. Then it's going to deal with the higher priority process, and it's going to execute that. Then once that is finished, it's going to go back to the other one. Yeah, so it stalls based on raw hazards. So read after write. So it's read after write because you're trying to read at the wrong time. So you read the wrong value because you're reading after another line wrote to the register. I think the here is based on the F4. And F0. So F4, so this one has to stall because F4. The other ones have to stall because F0. Structure of R4000 integer pipeline is through a 1x low delay. 1x delay is possible because the data value is available at the end of the S and can be bypassed. This delay is possible because the data value is available at the end of the S. Bypass. If the tag check TC indicates a miss, the pipeline is backed up a cycle. The correct data are available. Whatever. Pipeline interlocks enforce both the X1 branch stall penalty on a taken branch and any data hazard stall that arises from use of load results. After there are 4,000 implementations of MIPS processor made use of dynamic branch prediction. In addition to the increasing stalls for loads and branches, the deeper pipeline increases the number of levels of forwarding for ALU operations. In our RISC-V 5-stage pipeline forwarding between two register ALU, instructions could happen from the ALU memory or the memory write-back registers. For 1000 pipeline, there are 4 possible sources for an ALU bypass. Is 4. So I think that now is a lot more clear on my mind how it works, just based on control logic and signals between the lines. And then that allows them to synchronize depending what kind of situation it is. For the execution cycle should be different depending on the signals. So things all based on control on selection lines that are connected with multiplexers, and depending on what kind of hazard it is, it's gonna send a signal that's gonna make create a loop or something like that, or connect to some other structure on the hardware, like the station thing, reservation stations, or whatever the name of the that stuff is. So it's basically the same, always the same fundamental things. It's just different variations of the same fundamentals, just like programming languages as well. And obviously, this is probably because of the way space-time works, because everything is a multifractal. So the common stuff, the higher probability stuff, is going to be the parts of the multifractal that has highest frequency in relation to the observer. And the parts that are going to be like variations of that are going to be different scales of combination of the multifractal that have lower frequency in relationship to the observer on the present moment. That creates the illusion of past and future, because a holographic projection, which is the hierarchy of time, which follows phi, because that creates the torus. So I think the hierarchy of the pyramid creates the torus structure because it's going to follow a cycle, because it's a spiral. So like the projection of the observer creates the funnel of information, which is the hierarchy, which follows phi, which follows the cycle, because that's how infinity manifests itself on three-dimensional space through time. And this is so I think that this is getting close to the end here, because, or maybe not. Is it the same? Oh no, yeah. So there's still a bunch of stuff. So I'm probably gonna stop after when I reach the 5 here. I'm gonna stop. This is interesting to have. Maybe I should put this one outside there, because it's probably interesting to put this on codes on Godot at some point. Because obviously I'm not gonna remember all this stuff, all these formulas. This Amadeus law there, which is the formula that allows you to see how much you can speed up a program with parallelization, I think. I think I'm gonna do that. So I'm gonna put this one outside, so I remember. Put it here. Because obviously there's lots less images here. And once I'm done with all the folders, then I'm gonna finish the images on this thing. Then I move to the OS folder. I think the topics should review and these other topics here I'm gonna probably do upstream, so go one by one. And review resources, use ChatGPT as well, watch videos, stuff like that, until I finish all of them. The name of the stuff on the hardware is, I wrote down here, is interrupt. Yeah, advanced programmable interrupt controller. This is the parts. So it's the same pattern as the other ones. So for memory, it's gonna be the interconnection. And then for the interrupts is the same thing. Is like this stuff here is the thing that connects the different data paths with the interrupts. So it's basically signals going on the bus, and then that's what's changes the logic depending on obviously the state, the current state of execution. Hierarchy structure. Yeah, so the Linux book is the one that is probably one of the best ones from the ones that I read last time. Is Understanding the Linux Kernel. I think I have which is the book that I'm gonna read again. No. And there's another book that apparently is very good that they also talk about this Understanding Linux Kernel, which is the device. This is the next books that I'm gonna read here. So this is the book that talks about this advanced programmable interrupt whatever controller. And this book mentions these Linux device drivers, which I didn't read yet. So these are the next ones. So clock cycle per instruction. Oh. So one wafer, which is that disk of silicon that they use on the process to create the hardware, produces multiple dies. The die is the thing that actually goes into the hardware. So it's gonna be the final structure after the patterns and everything. So this is the last one that I'm gonna look. So I'm gonna stop here. I'm gonna look into the remaining pictures of this folder off stream. Then probably next time there's stream, I'm either gonna continue to review this stuff here. I think I might review some of them off stream, the images, or I'm going to do the stuff on that I'm doing there on Godot, which is to I'm basically recreating or I think eventually what I'm gonna do is just move, like gradually move, change Godot into something else probably. But I think initially it's just gonna be like a different system. I'm gonna change Godot enough so I'm able to do everything from C++ automatically. I'm gonna try to remove everything related to GDScript as well. And I might stream myself doing that, but I'm not really sure. So either I'm gonna continue to review this stuff or I'm gonna continue with the Godot stuff. And I'm probably gonna stream less. Yeah. So see you next time.